Okay, we said that although Rosenblatt proposed the perceptron, Minsky and Papert later showed that the perceptron is limited to only a certain kind of data configurations and does not work for data configurations beyond those kinds. And the example they used was the XOR gate. Let's try to understand that. We know that the ground truth of the XOR gate, the truth table for the XOR gate, is given by something like this, where if one of the inputs is 1, you get a 1, otherwise a 0. So from a perceptron perspective, what we would want is, in the first scenario, we would want your WXI to be less than 0 because we want the output to be 0. Similarly, these two cases, we would want it to be greater than or equal to 0. And in the last case, we want it to be less than 0 again. So let's analyze this. Let's take the first equation, which says W0 plus W1 into 0, which comes from here, plus W2 into 0, which comes from here. We ideally want it to be less than 0, which is what we want the perceptron to do, which means W0 has to be less than 0. Similarly, from the second line of the truth table, you have W0 plus W1.1 plus W2.0, which are the inputs in the second line. We want that to be greater than or equal to 0, which means W1 is greater than minus W0. Okay, so since W0 is less than 0, W1 would be a positive quantity greater than the absolute value of W0. Similarly, the third line in the truth table would similarly get you W2 to be greater than negative W0. And the final line would show that W0 plus W1 plus W2 should be less than 0, or W1 plus W2 must be less than minus W0. It's quite clear here that because W1 and W2 will be positive, W1 plus W2 cannot be less than minus W0, because we know that individually each of them are greater than minus W0, which itself is a negative number. Okay. W0 by itself is a negative number, so minus W0 will be a positive number. So we can see a contradiction in these criteria here, and that should clearly show you why a perceptron cannot solve the XOR problem. Also, visually speaking, you have the XOR problem to be represented as, you want these two elements, which are 0, 1 and 1, 0, to have a label to be 1, and you have these two elements 0, 0 and 1, 1 to have a label to be 0. And as we said, a perceptron simply embodies a line. And if you draw a line here, you're going to get this element wrong. And if you draw a line here, you're going to get this element wrong. And a XOR gate cannot be solved by a linear model. So as you can see, it's impossible to draw a line which separates the red points from the blue points here. And that leads us to the concept of a multi-layer perceptron. A multi-layer perceptron, as the figure shows, is not restricted, unlike a perceptron, to only an input layer and an output layer, but also has the convenience of including a hidden layer of neurons. The number of neurons in this hidden layer is a design decision. So here is an example of how a multi-layer perceptron can be used to solve the XOR problem. This is just one weight configuration that can solve the XOR problem. There could be other weight configurations that may solve or may not solve the XOR problem. All that we are trying to say here is that there is at least one weight configuration with a multi-layer perceptron that can solve the XOR problem. Let's look at this example. So you have the weights denoted on each of these connecting edges here, and you also have the bias given to be -1. So with these values given to us, let's take a couple of cases from the truth table and work out that this indeed gives a solution. So if you have 0, 0 as input, you're going to get 0 into 2 plus 0 into -1 plus minus 1. Z1 would get an input minus 1. Since it's a perceptron and its input is negative, it would give an output to be 0. You would get exactly the same output for Z2. You would get a minus 1 and its output to be 0, which means you're going to have what Y gets as 0, which we can assume that only values greater than 0 is the threshold is 0, and only values greater than 0 gives you a 1 as output. And you would get now, because the output at Y is 0, you would now get the output to be 0. Let's take the second case now and see how that works out for this particular scenario. So let's consider your input now to be 0 and 1. So if that be the case, your Z1 is going to get a 0 and a minus 1 and a minus 1, which would turn out to be minus 2, which means the output would be 0. And let's see what Z2 would get. Z2 would get a 0 and a 2 and a minus 1, which would be 1, which means the output of Z2 will be 1, which means you're going to get an output of 2 here, because 2 into 1 plus 2 into 0, which corresponds to a 1. Okay. You could hold, a similar thing would hold for the third row, third tuple, 1, 0. Let's rather work out the last one now, just to be sure about this again. So let's consider 1, 1. When we have 1, 1, you're going to have 2, minus 1, minus 1, which is 0, which means 0. Similarly, you would have a 2, a minus 1 coming from bias, a 0, a 0, 0, and a 0. You can work this out if this was fast, and you will notice that this is a valid solution for the XOR problem. You can in fact show that any Boolean function of n inputs can be represented exactly by a network of perceptrons containing one hidden layer with 2 power n perceptrons and one output layer containing one perceptron. So if you have a hidden layer, rather a multi-layer perceptron, and you have 2 power n perceptrons in that hidden layer, you can represent any Boolean function of n inputs. How do you prove this? We are not going to formally prove it, but informally it's fairly simple, because every case that you have can be represented as one neuron in your hidden layer. Remember, if you have n inputs, assuming you're talking about Boolean functions, there are 2 power n combinations, and you can ensure that the right perceptron clicks for each of those combinations. So you can come up with a weight configuration that ensures that each of those 2 power n perceptrons in the middle layer corresponds to one combination of n inputs, which automatically will give you your solution. It's fairly straightforward to see it informally at least. But one thing to keep in mind here is, while we say that any Boolean function can be implemented by a hidden layer with 2 power n perceptrons, this is sufficient but not necessary, which means you could solve a problem with less than 2 power n neurons too. For example, we just now saw the XOR problem, which we solved with a hidden layer with just 2 hidden neurons. Ideally, according to what we said in the next slide, we should have needed 2 power 2 or 4 neurons, but that's not the case. And that's the reason why we say that a network of 2 power n plus 1 for the bias, is not necessary, but it is sufficient. You can make do. You can probably find solutions with even lesser, but you can definitely find a solution with 2 power n neurons or perceptrons in the hidden layer. Why does this necessary and sufficiency matter? The reason is, as n increases, the number of perceptrons in the hidden layers increases exponentially, 2 power n. So your multi-layer perceptron can become too computationally intensive to train, or to even just to take a forward pass through. So you don't want that always to be too computationally intensive. You ideally want to find the multi-layer perceptron solution that has least number of neurons in your hidden layer. Now let's ask the question, what do we do if we want to go beyond binary inputs and outputs? We only spoke about Boolean inputs. We did say that perceptrons could handle inputs beyond binary, but are there any relationships that we understand? The previous result that we showed was only that a multilayer perceptron with 2 power n hidden neurons can solve any Boolean function. What if that function was not Boolean? Can we use the same perceptron model to represent such functions? The answer is we need something called activation functions. Why activation functions? We'll see that in a moment. So far we noticed that a perceptron only fires when the weighted sum of its inputs is greater than a threshold minus W naught, or which was 0, which was theta. So this thresholding logic can become very harsh at times. For example, if your minus W naught was 0.5, even 0.49 and 0.51, which are very close to each other, will end up giving very different results because one of them is below the threshold and one of them is above the threshold. Which means your thresholding function is a step function where you have a sudden change in your output even with a very small change in your input. Typically, this behavior does not occur in the real world, but even in this case, the behavior is not a characteristic of the problem. It is more the characteristic of using a step function as a thresholding function. And we all know that in the real world, you generally expect a smoother decision function, such as the one shown in red here, as you go from one value to another value. You don't want it to jump up. You do not want the output of the perceptron to be 1 suddenly when the value goes from 0.49 to 0.5 or 0.499 to 0.5. How do we handle this? The way we handle this is to introduce what are known as activation functions, which aim to replace the threshold function that you have with more smoother functions. And one early example, which was used for several decades, is known as the sigmoid activation function. And a perceptron or a neuron that uses a sigmoid activation function is known as a sigmoid neuron. You ideally could use any logistic function which has a shape such as this, to obtain a smoother output function than a step function. The one that we are particularly going to talk about here is the sigmoid logistic function, which is given a input Wx, which can be expanded this way. The sigmoid function computes 1 by 1 plus e power minus that input. That's your sigmoid function, which in a graph form has this particular shape. Clearly here, you no more have a sharp transition at a threshold, but a smooth transition that goes as your input keeps changing. Also, your output now is no longer just binary. It's not just 0 or 1, but your output now can be any value lying between 0 and 1, which could potentially be interpreted as a probability of the output. So, which means if you used a sigmoid activation function on the neuron in your output layer, it would give you a value between 0 and 1, which can associate a probability with whether a point belongs to the positive class or a negative class. So if your output was 0.5, you would perhaps, not 0.5, let's take another example, let's say 0.6. You would say that, assuming your inputs are say patient records, you would say that this patient has a 60% risk of say suffering from cancer or heart attack, or whatever problem you're modeling in this particular scenario. More importantly, unlike the step function, this function is smooth. It's continuous at minus W naught, which is your threshold. It is continuous there, has no discontinuities, and is also differentiable. Why is this important? We will see very soon. It being differentiable is extremely important for how we're going to train these kinds of networks. There are other popular activation functions. We briefly review them here, but we'll cover them in detail in a later lecture this week. But a sigmoid activation function, we just said, is given by assuming your input is z, is 1 by 1 plus e power minus z. Tan h, as we know, is the hyperbolic tangent, which is given by that formula there. There's also an activation function called the rectified linear unit, which, if you see here, is the blue line, which is the blue line on this particular graph, which is given by, if your input is z, the output is max of 0 comma z. So if your input is negative, it would give you 0. If your input is positive, it will give you the value itself. That's a very, very popular activation function. There is also a variant of the ReLU activation function called the leaky ReLU, which does not make this 0 but keeps this a very small value, and we will see each of these, the design for each of these, a little later this week. A more general variant of the ReLU activation function is known as the exponential linear unit, or ELU, which is simply a smooth form of the ReLU or the leaky ReLU activation function, which is given by alpha into e power z minus 1 comma z max of that, where alpha is a number greater than 0. And you can see the ELU activation function in the purple color on this particular graph. We will see these activation functions a bit later in detail, but all that we are trying to tell here is that the activation function is important for us to understand how well multilayer perceptrons can model non-binary data, non-Boolean data. And that's where the representation power, the study of the representation power of multilayer perceptrons, MLPs stands for multilayer perceptrons, comes in. A very well studied, very well cited theorem is known as the universal approximation theorem, which states that a multilayer network of sigmoid neurons with a single hidden layer can be used to approximate any continuous function to any desired precision. Okay, this is a fairly strong statement. We are saying that if you give any continuous function, we can use a simple multilayer perceptron with sigmoid neurons and one hidden layer to approximate that continuous function. We are not going to formally prove it here. If you are interested, these papers cited here are good pointers to the proof. There's also a very nice visual explanation of the universal approximation theorem in chapter 4 of Michael Nielsen's online book on neural networks and deep learning. So your homework for this lecture is try to solve XOR using a multilayer perceptron with 4 hidden units. Come up with your own weights and solve XOR using a multilayer perceptron of 4 hidden units. This should also help you understand the theorem that we spoke about how any Boolean function can be represented by a multilayer perceptron with 2 power n hidden units. This should also help you get an intuition of that. For further readings, please also feel free to refer to Mitesh Kapra's original lecture slides, which are on the website linked here. There are other good resources. Deep Learning Book, which is publicly available on a website called deeplearningbook.org, is a general resource that we will point to for various parts of this course. Chapter 6 is a good introduction to multilayer perceptron. There is also the Stanford CS 231M course, which is also a good course, whose notes are also relevant here. There is also the Stanford UFLDL tutorial and a very nice introduction to neural networks by Raul Royal. Here are some references, and we'll stop here for now.